Okay, so today's lesson is topic 4 and 14, which is essentially all bonding in IB chemistry. And so the first section we're going to be doing is dividing this up into types of bonding and comparing and contrasting those types of bonding according to different descriptors. And so we will break this up into 4 columns. We'll have a descriptor, and then we will have ionic bonding. We will have covalent bonding, and then we will have metallic bonding. And so we are going to compare and contrast these based on different aspects of each one, okay? And so the first thing that we should always start with is the definition of each type of bonding. And there are similarities and there are differences between that. And so the first row we'll have is definition of ionic versus covalent and metallic bonding. Now, every definition of bonding starts with electrostatic attraction between. So each of these definitions starts with electrostatic attraction between. So I'm going to put that over in the descriptor so you don't have to write it a bunch of times here for each one. And that'll save you a little bit of space as well. Okay. So an ionic bond is defined as the electrostatic attraction between oppositely charged ions. Okay. So you have your cations and your anions. A covalent bond is defined as the attraction between a positive nucleus and a shared pair of electrons. Okay. Please do ask questions if there's anything that I've written that might be confusing or anything like that. Metallic is defined as the attraction between cations and delocalized electrons. Okay, so that's the definition of each type of bonding. And so if they ask you this on multiple choice or short answer, that's what you want to see when that's what you want to say when they ask that. So there's always a attraction between two different things, a cation and an anion, or a positive nucleus and a shared pair of electrons, or cations and a delocalized sea of electrons. I wouldn't just say the word sea, I would say delocalized. Yes, Alexandra. Delocalized means not owned by any specific atom. And when we get into metallic bonding a little bit later and we talk about the properties, so the way a metallic bond works is that the electrons are spread around all the cations, and no metal ion owns those certain electrons. And so they're equally shared throughout all the atoms of metal, and that's what holds it all together, kind of like a glue. So that will be our next diagram here. Okay. So our next descriptor will be a simple diagram. Okay, so if I had to draw a simple representation of this, an ionic bond would look like this: a positive ion and a negative ion attracted to each other. No. Generally, I do this as generally cations are generally smaller than their atomic radius, so that's why I drew it smaller. And generally, negative ions are larger than their atomic radius, so I drew that bigger. So it's not really important, but it's something subliminal that I kind of implement in my drawings. In a covalent structure, what you have is a positive nucleus and that attraction for the shared pair of electrons. That interaction is what represents the covalent bond that's happening. So when two atoms share a pair of electrons, both their nuclei are pulling on those electrons, and it keeps that bonded together. Okay. Whereas if you had to draw a metallic, what a metallic bonding is are positive ions, cations, surrounded by delocalized electrons. So those electrons aren't owned by any specific atom, they are just contributing to the entire bonding structure. So hence the word delocalized. And that's what gives it certain properties and things like that. And we'll talk about those properties a little bit later. Okay. Questions on any of the diagrams that I've drawn here? Okay. Okay. Next, we're going to go into physical properties. And so characteristics of each type of bonding broken out into certain categories that you need to address for each one. Okay. So this relates to the attraction or the strength of the attraction between the ions and the molecules and things like that. And so the first one we'll do is conductivity. Okay. Conductivity depends on the presence of free moving electrons or ions in the substance. Okay. So free moving ions or electrons in the substance. Okay? And so each one can have conductivity or not. And depending on the state of matter, it can matter. For example, ionic compounds are conductive when they are aqueous or liquid or gaseous. Okay. Because when you dissolve an ionic compound in water, or you melt it, or you make it into a gas, it separates all the ions apart. And when the ions are now freely moving on their own, electricity can pass from ion to ion in that substance. But it is non-conductive in your solid state, because when it's solid, all the ions are fixed in a crystal lattice. And that means that there is no movement of ions that allows electricity to pass through. So like solid salt does not conduct electricity, but salt in water does conduct electricity. Okay. Or molten salt conducts electricity, which we talk about in topic 9 with electrolytic cells. But you do want to know the conductivity characteristics of each of these types of bonding. Okay. Covalent bonding is generally non-conductive because there are no ions and there's no electrons that are being mobile. They're all being shared between the atoms within a molecule. And metals are always conductive. Because of those delocalized electrons, that allows electricity to pass through the substance. Questions so far? Sure. So remember, to have conductivity, you have to have free moving ions or electrons. But in a covalent bond, the electrons are secured between the two atoms when they're sharing. So those electrons cannot transmit electricity. And because they're sharing electrons, there's no ions being produced in this covalent molecule. So there's no way the electron could pass through that either. Oh, that is because of the salt and the sweat that your body produces. And so, like, that's the same idea with a bathtub, right? Like, bathtub electrocution is because when you sit into the water, or even if it's like tap water, there's ions present. There's metal or other different salts in the water. And so if you put electricity through there, it will pass through you, and your body's conductive of electricity as well, because your body's essentially a whole aqueous solution of ions and stuff like that. So that's kind of how you get electrocuted from that. If you threw a toaster into distilled water, nothing would happen, because distilled water has no ions, it has no free moving electrons. There would be nowhere for the electricity to pass through. Correct. Yes. And you know someone has used their hair dryer in a bathtub and electrocuted themselves, and that's why we have the safety labels that we do now. All right. Volatility, okay? The term volatility implies ease of evaporation, okay? So don't think of volatile as explosive. There is some connection, but it's not the direct definition of volatile. You know, this is one of those cases where the chemistry definition of a word is very different than the kind of common English definition of a word. Like when you say someone's personality is volatile, you mean it's like very explosive or very kind of dangerous. But volatile in itself just means that it evaporates very easily. Now, a lot of things that evaporate very easily are flammable or explosive, and that's why there tends to be a kind of connection between the two, but it's not always true. Okay. And so with ionic compounds, they have very low volatility, okay? Because they're generally solid ionic lattices. Oops. With very strong attractive forces, which means they have a very high boiling point, okay? Actually, you don't need to really draw that line, but so they have a very high boiling point. In fact, you'd kind of rank ionic bonding as one of the strongest of these three bonds in question. Okay. With covalent, you have medium to high volatility. And so you have low boiling points here relative to ionic and metallic bonding. So because this has weak intermolecular forces, which we'll talk about a little bit later. Okay. So covalent molecules, because with ionic bonding, the intermolecular forces are the same as the bonding forces. That's what holds it all together. But with covalent molecules, you have the bonds within, but then you also have the weak attractive forces amongst the molecules. And that's what's trying to break. And that's a lot easier to break than a covalent bond. Like when you boil water, you don't break up water into different atoms. You just separate the water molecules from each other. And that hydrogen bonding is still relatively weak compared to even like ionic or metallic bonding. So water's boiling point is like 100 degrees Celsius, whereas ionic compounds don't really start to boil or melt until thousands of degrees Celsius. So that's the big difference between that. So yes, you say hydrogen bonding is a strong IMF relative to the other covalent molecule IMFs, but in the whole spectrum, it's very still low. Okay. Metallic, low to medium. I would probably say low for the most part. Oops. Yeah, I mean, yeah, I think I'm going to stick with low here. Low volatility, and so they usually have high boiling points. Okay, and so not as high as ionic compounds, but still fairly high relative to covalent ones. Questions so far? This is a long chart. I apologize in advance, but this is it's a lot of writing. Huh? Quite a few. Maybe a 2-page chart, yes. Did you not spread out your columns more for doing it sideways? Oh, okay. You just write big. Okay. Emma, how far are you on your chart? Okay. We still have a little space, I think. Okay. I'll try to make these a little more compact. Okay. Solubility. Okay. So usually what we mean here is with water. Okay. And so with solubility here, most ionic compounds are soluble. Yes, there are a few that are not, but in IB, you don't need to know solubility rules. You don't need to know which ones are soluble or not. But we're going to assume that the ionic compounds we deal with here are soluble, unless otherwise stated. Okay. In covalent bonding, polar molecules, yes. Non-polar, no. Because water is a polar molecule, so it interacts with other polar molecules and dissolves them, or mixes with them, but they don't interact with non-polar molecules. So like oils and stuff like that are non-polar, they're not soluble in water. So there's a mixture here. Okay. Metals, I'm also going to say non-soluble. Okay. Thankfully, metals don't dissolve in water. They might react with water, but they don't dissolve in water. Okay. Naming. Okay. Just a quick refresher on naming. We're not going to spend a lot of time on this, but to name ionic compounds, you go with the cation first, and then the anion second. Okay. And if it's an element, you change the ending to IDE. So here, if it's an element, you change to IDE. If it's a polyatomic, you leave it alone. Cations, you should never change anything to the name. So the positive ion, whether it's metal or even a polyatomic, you don't ever change the name. The only time you change the name is if it's an element, anion, and you change to IDE. Sulfide, oxide, chloride, all that stuff. Okay. Now, you may have a Roman numeral. Okay. As well, depending on if you have a transition metal. Because transition metals, you have to identify and tell what the oxidation number of them are when you name. Okay. Covalent, it's 2-part. So element 1, element 2. And in this case, you always change the second element to IDE. Okay. Yes. Oh, if the anion is an element, like it's a negatively charged individual element, you change the name of that ion to IDE. So when I say oxide ion, I mean O2 minus. Yeah. In covalent, you keep all the names the same except you change the second one to IDE, and you use prefixes. Let's see, prefixes on both elements except mono on first. So you use all the prefixes: mono, di, tri, tetra, penta, hexa, those prefixes, except you never put mono on the first element. So the one I like to remember for that is CO, because we call that carbon monoxide. So that reminds you that you don't put mono on the first one, and you do put mono on the second one. So I like that as a reminder for naming. Okay. For metals, there's no naming convention. Well, you just name it like the way you do element. So like you don't change any names, you don't say anything, you just say the metal. So you say potassium metal, you say sodium metal. So there's no special naming, no. So that's good news. Don't worry, he's doing his experiment. Everything's gonna be a 5. He has to he's making model rocket like like engines, so he has to compact the clay and all the chemicals into a PVC pipe and then ignite it, and it combusts, but he has to pack it very tightly so that it combusts consistently. So he's like hammering it to pack it in. That's what you're hearing. Yeah, that's pretty cool. He's had pretty good success so far. Hasn't burned anything down yet, so that's a good thing. Okay. In case I live to regret that, the person making the model rocket engines is Nicolas Alonso Sancho. Just in case this for recorded for um, yeah, recorded for posterity. That's the word I was looking for. Okay. All right. Last column for this. Okay. I know, but this one is kind of a lot of stuff. Okay. Well, okay. So special. What I'm saying here is this is specific for each type of bonding and it only pertains to that. And so that's why I kind of make this last column special stuff that only applies to each one. Okay. So ionic, you need to know polyatomic ions. And there are 10 the IB specifically says you need to know. Okay. So that is ammonium. Let's see, hydroxide. Oh, special. So this is specific to each thing. Hydroxide, nitrate. I'll write the formulas next to it in a second. I'm just going to write all the names first. Hopefully you are starting to know those names, but the formulas. But hydrogen carbonate, okay. Carbonate, sulfate. Oh, I'm going to run out of room. All right. Phosphate, ethanoate. Oh, I'm going to run out of room. That's really okay. Nope, we just move up. Plenty of room. Look at that. Okay, it is cheating a little. Okay. Cyanide and dichromate. Look at that. Like a glove. Okay. So these are the 10 polyatomic ions you need to know naming and formula wise, and that is an expectation for the IB exam. So you have to know the formula, the charge, and the name. So ammonium, the only positive ion, NH4 plus 1 charge. Hydroxide, OH minus 1. Nitrate, NO3 minus 1. Hydrogen carbonate, CO3 minus. Carbonate, CO3 2 minus. Sulfate, SO4 2 minus. Phosphate, PO4 3 minus. Ethanoate, CH3 COO minus. Cyanide, CN minus, and dichromate, CR2O7 2 minus. Yes, this is something that you have to know for the IB exam. Any other ions they might use, they're obligated to tell you what the names are because the IB literally says you must know these 10 polyatomic. It says students should be familiar with the name, formula, and charge of the following polyatomic ions, and these are the ones they list. So these are the 10. Anything else is not mandatory to know. So you don't have to know permanganate. You don't have to know chromate. They will have to tell you. They're obligated to tell you the formula for those. If they ever did that, then that would be something that teachers would complain to the IB about on a question. It'd be kind of a protest thing, not like a physical protest. It would just be a digital protest. Because whenever after the exam is taken, teachers get to see the exam 3 days afterwards, and so we get to look at it, and then there's an online forum where we can protest questions and stuff like that, saying like this question is not fair or it's poorly worded, um, and sometimes they'll take that into consideration when they omit questions on exams and stuff like that. There have been questions in the past where they omit a question for multiple choice or a mark for a short answer because they realize it wasn't a fair question. SO4 2 minus, yes. Okay. Sorry, do you still need to write phosphate the rest of it, Sammy? Okay, no, it's okay. You sure? Okay. Now, for covalent, the special thing you need to know about are network covalent molecules. Okay. And this is going to take I'm not going to be able to fit everything in here, but I'm going to say a few things and you can kind of look at them a little bit later. But this is that group of network covalent molecules are ones where you don't have hydrogen bonding or LDFs or dipole-dipole. Everything's covalently bonded. So what we're talking about here in this category is diamonds, yeah, graphite, and fullerenes. Okay, so you that's something that you kind of have to think about in this kind of aspect here. So understanding the properties of diamond, graphite, and fullerenes, and understanding the structure of them, that's going to be a big thing. Now, the other one they love to deal with is silicon dioxide. Okay, SiO2, because SiO2 is very similar to diamond in its network covalent characteristic, but it's deceptive because if a student doesn't know the structure of SiO2, they might think it's just like CO2 because Si is in the same group as carbon. So why does it not bond the same way as carbon? Because it's bigger, it tends to not have the ability to form the double bonds like carbon does. And so silicon dioxide actually looks like this. Yeah, it forms a network of Si's and O's. And you'd ask yourself, well, why is it called silicon dioxide if each Si has 4 O's? Well, what do you know about each of those O's? What is it actually doing? 2 silicons, exactly. So the ratio is 1 to 2, even though there's 4 oxygens to every silicon because each oxygen is bonded to 2 silicons. So the ratio is really 2 to 4, not 1 to 4. And that's why, like, this one's very tricky, SiO2. So that one I definitely would kind of be familiar with. That's what sand is made of, and that's what quartz is made of. All minerals and stuff like that. That's silicon dioxide. And you can melt this and then make glass. That's how you make glass. Like traditionally, you make glass from silicon dioxide. You melt sand down, get rid of all the impurities, and then you're left with this crystal and kind of transparent layer. Okay. I'm going to put one thing here, but we're going to talk about this when we talk about Lewis structure, so don't worry too much about it. Coordinate covalent bond. Just fit it right in there. Coordinate covalent bonding, we'll talk about when we get to Lewis structures. So for diamond, graphite, and fullerenes, you need to know A, how many carbons are bonded to each one. B, which ones conduct electricity. That's just graphite. And for higher level, you have to know hybridization. But those are the main like general structures. So let me put a diagram in here that you can refer to later on, but it's not going to fit in here. But so this is a good diagram of all the different like. Actually, I'm going to put 2 diagrams in here. One will be of the SiO2 and one will be of the fullerenes and stuff. So let me like weak LDF forces, yes. Yes. Okay. So I'm putting this in here so you can refer to it. Obviously, I don't want you to draw it right now, but you could go back to the notes and kind of download this. But this is the different carbon allotropes: graphite, diamond, fullerene, and then SiO2 in a more colorful, more accurate drawing than mine. No, but this picture helps you understand how many carbons it's bonded to each time and what kind of general shape is. So I would be able to recognize those shapes at least. Okay. Metallic bonding, okay? One, the term non-directional bonding, okay? Non-directional bonding means exactly that. The bonding is not in a specific direction like in ionic or covalent bonding where like you know what's attracted to what. It's kind of omnidirectional. It's attracted to every electron surrounding it. So there's no like it's bonded like in this direction and this direction, and that's the only way it attracts. No, it attracts all the way around. So that's what gives it the ability to be malleable and ductile. Because the non-directional bonding exists, when you apply a force to it, because the bonding isn't directional, it allows things to move out of the way. It allows it to flatten or allows it to bend or stretch. And so that non-directional bonding is what gives those metal those unique characteristics for it. So that's what makes metals malleable and makes them ductile. Whereas if you hammered a ionic crystal lattice, it would just shatter. It would just break into smaller pieces. It's very brittle because everything's in a fixed direction. So if you apply a force, that direction will fight against it, and you'll break that attraction, and that's why it kind of shatters into little pieces. Okay. The second idea is alloys. Okay. An alloy is a mixture of a metal with a metal or non-metal. Okay. I just realized there is one more row I wanted to do with this. I'm trying to think if there's a place I can fit it in here. Oh, I just thought about it. We're gonna have to add another row. I'm sorry. Because the one thing I didn't talk about is the factors that affect the strength of the bonding, and that is kind of important. Actually, you know what? No, I'll say that for IMFs. We'll just say that for IMFs. Okay. So, all right. Alloys. Okay, so they provide enhanced properties. And so an alloy is a mixture of a metal with another metal or another non-metal. And you don't have to go really into detail of the types of alloys, but like brass, for example, is an alloy of copper and zinc. So copper and zinc separately have different characteristics than a mixture of copper and zinc to form brass metal. Or steel is a combination of iron and carbon, and it has different properties than iron itself. It's less malleable, but it's stronger and more rigid. Okay, so there's some benefits to making alloys that are not that give it different properties than the individual metals themselves. Okay. So know the concept of alloys in their general sense. So maybe know a couple examples like steel and brass and the fact that they make them more rigid and stronger, less malleable in that case. And it really depends on how much carbon you infuse in it. Like there's different levels of steel, and they like call them by ratios. They call it like 80-20 steel or like 82-18 steel because it's how much iron and carbon is in the mixture. Questions? Okay. That is a table of all the things you need to know about ionic, metallic, and covalent bonding. Hopefully you recognize some of this stuff, but a little bit of a refresher never hurt. And I think organizing this way helps you kind of see them in contrasting characteristics. Any questions about any of these boxes? CR2O7 2 minus. Yeah. Okay. You can go back to normal page vertical now. Okay. Okay. All right. Just one last check. Any questions on anything I wrote in this table of comparing and contrasting? Okay. Okay. We are going to do Lewis structures now because I think Lewis structures are really important. And I'm going to show you how to do Lewis structures, and that will spawn off a couple of different issues with the challenges of Lewis structures that I think this method solves for drawing Lewis structures, okay? And it's a little bit sometimes hard to digest, but I think it'll be beneficial for you to understand this because it'll help you prevent you from making mistakes like the other ones, like the other methods of doing it, okay? Okay. So my method of drawing Lewis structures, it sounds like it's a little bit of trial and error, but it's not. The method is consistent every time that you do it. Okay. My style of doing it is not drawing every single element individually, drawing their valence electrons, and then trying to pair things up because that works sometimes, but it doesn't work other times. There's issues with that type of drawing out because sometimes the electrons don't pair up right, because there's coordinate covalent bonding, or there's an expanded octet, or there's resonance, and you may not see that when you're trying to just pair up electrons. So this way eliminates those concerns, because what you do is essentially you determine the budget, okay? Essentially, what is the number of available electrons in your structure? So every time you do this, you determine, okay, how many electrons do I actually have to use for my structure, okay? Okay. You identify which elements need an octet, okay? So the way you do this, you have to say, okay, which elements actually need an octet, which ones don't, okay? Every element with 4 or more valence electrons needs an octet, okay? So any element that's in group 14 or further right will always have to have an octet at least in your structure. Okay. And lastly, what you do is you draw a test structure. That test structure represents the maximum number of, actually, let me erase that. Sorry, let me rephrase that because I can see how it would be confusing. Okay, test structure assumes all single bonds and octets are present. Okay, the test structure is not always right. It's your starting structure, and it may be right, it may not be right. Okay, and then you change the test structure to match the budget. Okay. And I know this is a lot of words and you haven't seen it in action yet, so it's a little bit confusing, but I wanted to outline the steps, these ideas, before we actually do it so you can kind of see what I'm talking about. So we have to determine the budget. How many electrons do we have in our structure? See which ones need an octet. Then draw the test structure out with the most basic number of bonds and electrons you can have. And then if it doesn't match our budget, then we have to change it by adding bonds or adding lone pairs to make them match. Okay. So for example, one of the structures that students struggle a lot with is carbon monoxide. Because when you draw carbon monoxide, it's not obvious how things bond, because when you draw carbon monoxide, you get 4 electrons and 6 electrons. And you've been told, oh, I need a pair of unpaired electrons. Okay, that's fine. 1, 2. And you end up getting a structure like this. But that's wrong. That's not the right structure for carbon monoxide. And so this is an example of where drawing valence electrons doesn't always work. Now, if you do my method, it will get you the right structure because of this. When I look at CO, carbon has 4 valence electrons, oxygen has 6. That means I have 10 electrons for my budget. So my structure can only have 10 electrons total in my structure, bonds and lone pairs all included. Okay. Now, carbon needs to have an octet, and oxygen needs to have an octet because they both have 4 or more valence electrons. Wait, why is my, I don't know why my panel's going on. Okay. So they both need an octet. So what I'm going to do is this. I'm going to draw it as simply as possible with everything having an octet. Like I said before, this is not necessarily the real structure. This may not realistically work, but you have to start from this and then build off of that. So this would be the scenario if it was singly bonded and everything had an octet. Okay. Now, how many electrons does this structure have? 14. Okay, that can't work because we only have 10 to work with. Okay, what that means is we have too many lone pairs here, and that some of these lone pairs are actually bonds between the structures here. Okay, so what we have is we have 4 extra electrons that need to be transformed into bonds. Okay, and every bond is 2 electrons. So that means we need to convert into 2 bonds. So what happens is carbon gets a triple bond with oxygen, and you're left like that. And this is our 10 electrons. And there's our final structure. Yes, Marina. No, you should not. That's a good question. Sometimes I teach this, I divide by 2 just because every pair is like 1. That's fine too. Like I think in previous years I would say, okay, this is 5 pairs and this is 7 pairs. So I need to bond twice. That's fine too. But no, you should never have a structure that has an odd number of electrons. That's a good question. And you have to remember to factor in your charge as well. If there's a charge, you have to do that as well. So you see how in purple, you're not going to get that structure, but you will get here, because what the purple doesn't tell you is that one of these bonds is coordinate covalent, which means that one atom donates both electrons to the bond. Because carbon doesn't have enough electrons to be able to bond sufficiently to get an octet. Oh. So for clarification, when you convert things into bonds, you eliminate 2 possible lone pairs because those lone pairs aren't needed separately anymore. They're shared as one pair of electrons between them as a bond. So what happens here is when you convert this, this becomes now this. And then this becomes now this. So yeah, 2 lone pairs equals 1 bond. That's effectively the same because 1 bond means both of them can claim 2 electrons in them instead of having 2 separate pairs of electrons. That always works. Okay, it always works. Okay, but so what this means is because oxygen has more bonds than it normally wants, because oxygen only wants 2 bonds because it has 6 valence electrons. That means one of those bonds has to be a coordinate covalent bond. And that means that oxygen is donating both of its electrons to that bond and they're not sharing, they're not each sharing one, because carbon doesn't have any to share there, right? Because carbon, like if you think about it, carbon has 1, 2, 3, 4 electrons, and like those two are the two in the first two bonds. So those last two electrons have to come from oxygen, because you see how oxygen, you have to account for the 6 electrons of oxygen, a lone pair, and 2 in the first two bonds, and the last 2 are the last bond. Does everyone see how I did that? Okay. You want it so that your structure in the end matches your budget. That's the whole purpose. Matches the budget. So matches the number you calculated that you have to work with. And this works because that purple one has 14 electrons and you only have 10 to actually work with. So you have to get rid of some of those lone pairs and start sharing them to lower the number of electrons you are drawing. So then how do we, like, how do we determine in that problem if it's coordinate covalent? You determine it's coordinate covalent because generally the atoms that are coordinate covalent have an expected number of bonds. And so you can look at the valence electrons there. So oxygen, because it has 6, generally has 2 bonds. So if it has more than 2 bonds, there's a coordinate covalent bond somewhere. Nitrogen has 5 electrons, which means it has 3 bonds usually. If it has 4, that's a coordinate covalent bond. Oxygen and nitrogen are usually the ones that have coordinate covalent bonds for Lewis structures. Okay, that's a good question. Okay. Does everyone see this a little bit more now? I'm going to do another couple examples because, again, this takes a little time to absorb, but I think it's really useful for all y'all trying to figure out structures and stuff like that. One that you know, but I still want to use this example because I think it's applicable, is CO2. Okay, I think for most of y'all know what CO2 looks like, but I'm going to use this example to demonstrate that. Okay, CO2, carbon has 4 electrons, oxygen has 6, and there's 2 of them. So that means we have 16 electrons to work with. Okay. Now, because carbon has 4 and oxygen has 4, that means they both need octets. And carbon's generally the middle atom. Usually the first element in a covalent molecule is the central atom. So we draw it out like this. Everything has an octet. Again, this is a test structure. It's not always meant to be the right answer to start with. It's where it's the baseline, and then you manipulate that to reach the final answer. Okay. Okay. So how many electrons do we have on this test structure here? 20. Okay. Which means you have 4 too many electrons here. So that means you need to add and convert 2 bonds to reach 16. Okay. What's the best way to do that? How would you distribute 2 bonds? Yes, Lucia. Right. So you do a double bond between one CNO and then another double bond between the other CNO. Okay. So this becomes CO2. One second. Okay. Sorry, the video is going to be very confusing. So I forgot where I was. Okay. That's awkward. Okay. I forgot to hit resume recording. Yeah. So with CO32 minus, you get 24 electrons. But when you draw out CO32 minus, you get 26 electrons, which means there's one extra bond. But all 3 locations are identical. So you don't place the bond in any one spot because they're all the same. So what happens is they actually exist in all 3 spots because they're equivalent. And that's the definition of resonance. So that double bond rotates, they're delocalized electrons that move from one carbon to oxygen bond to one carbon to oxygen bond consistently throughout. Okay. Questions about that? This also works for expanded octet, but I'll save that for the higher level section because you're going to realize when you draw the test structure of expanded octet, you don't have enough electrons, which that means you need to add lone pairs to the central atom to make up for the lack of electrons because you don't have enough electrons. And so it also works for expanded octet as well, which is really handy. Yes, that's HL. Yes, draw the arrows around that as well. So the way I drew it here is the way the IB expects you to draw resonance structures. Include the charges and the brackets. Tana, you all right? I would say 3. Yeah, I don't think there's really resonance for 4. So 3 is usually it. Most of them are 2, and then just a few of them. I think carbonate's really the only one that's really 3. Now, one thing you have to understand about resonance, and I kind of touched upon this earlier, is that, oops, did I miss chat? Oh, thank you, Andrea, for reminding me that I didn't record. I stopped recording, so.
Do they know where
No, it's okay, but it wasn't that long ago. Okay. So what you need to understand about resonance is because the electrons are delocalized and moving around, they're not the equivalent of one full bond. So when you compare CO3 2 minus to CO2, no, this is SL. How did I hear you? I know. Okay, it was pretty quiet. So okay. So it was a pretty quiet room. I mean, I think everyone heard. Like, did y'all hear it? Okay. All right. So I'm not gonna even address that comment. Okay. Um, here's what you need to understand. Okay, the CO bond here is weaker than this CO bond because the right CO bond is essentially a bond of like it's a double bond. So this is like a bond value or bond order of 2, meaning that there's 2 equivalent bonds between that. But in CO3 2 minus, it's not equivalent of 2 bonds. What is it really equivalent of each one? If you had to guess what the equivalency of each bond is when there's one being divided across all 3, what do you think the average bond value is there? Distribute that double bond around all 3 spots. What do you think the bond order would be? No, it's it's 3 spots though, Alexandra. So each one gets how much of the bond? If you distribute them equally, a third. So this is the equivalent of a 1.33 bond order. All right, apparently. So the double bond distributes itself equally across all 3 regions. So each bond is effectively 1.33 bonds. Yes, that is a way to think about it. Yes, Marina. That is the right way to think about it. I just hadn't said that yet. Yes.
the bond values, like they're not going to be like 1.33, like actual like the right?
Yes, they are.
They are.
Well, here's why this is important because there's a thing about bond strength and bond length and things like that. When you have a 1.33 bond order, what that tells you is it's stronger than a single bond, which is a bond order of 1, but weaker than a double bond, which is a bond order of 2. So if I looked at the energy it took to break a bond in CO3 2 minus, it would be less than CO2, but it'd be greater than a C single bond somewhere else. Like that's what you want to understand. So a bond order, like Marina said, the best way to think of bond order is number of bonds divided by number of atoms bonded. That's bond order. And so for CO3 2 minus, it's 1.33. For CO2, it's 2. Okay. So the higher the bond order, the stronger the bond, the shorter the bond length, okay? Right? Because the stronger the bond, the more it pulls the atoms closer together, and so therefore it has a shorter bond length. But all those things are related to each other. And the IB likes asking about that too. SL or HL, because this is an SL topic. We're not done with SL yet, but let's take a 5-minute break. This has been a lot of information to kind of process, and I'm going to take a 5-minute break. We'll start in 5 minutes again, and this gives people to ask an opportunity to kind of ask some questions off recording as well. So I'm going to pause recording. So once you get Lewis structures, you can then determine shapes, and so that's what our next section is about, VSEPR. Or VESPR, depending on what textbook you talk about. But it's valence shell electron pair repulsion. No, but I'm just kind of putting it out here. Okay. What it means is that atoms organize themselves around the central atom to minimize repulsion. That's the purpose of it. So you get these general shapes that occur with these molecules that are covalently bonded that we have named. Okay. And so they do this to minimize electron pair repulsion. So they orient themselves to minimize that. Now, what you need to know is that lone pair repulsion is the strongest. So you want to keep the lone pairs away from each other as much as possible. Then it's lone pair, oh, sorry, there's no dash here. And then bonding pair. And then it's bonding pair and bonding pair. So atoms are the ones that get pushed together as close as possible, and lone pairs get the priority when they're trying to spread out the molecule. Okay, so lone pair is the strongest repulsion. Lone pair, bonding pair is the second one, and then bonding pairs with each other are the lowest one. Okay, so term you need to understand, electron domain. Okay, an electron domain is defined as essentially a bonding region or a lone pair. Those are all your electron domains. And so when you draw the Lewis structure out, you can see how many bonding regions or lone pairs it has present. Now, a bonding region doesn't matter how many bonds are present in that region. So it might be a single bond, double bond, or triple bond. You treat them all the same. So a bonding region doesn't matter how many bonds are in between there. It counts as one. Okay. Okay. Another terminology, electronic geometry. Okay. Electronic geometry is the shape of the molecule if all domains were bonds. Okay. So the electronic geometry is the shape of the molecule if you treat every pair of electrons as if it were a bond. So they're equivalent. Whereas molecular geometry is the shape of the molecule shape of the molecule factoring in lone pair repulsion. So every electronic geometry is a molecular geometry, but not every molecular geometry is an electronic geometry. Okay, so there are fewer electron geometries than there are molecular geometries. Okay. So let me demonstrate what we're talking about here. okay, with examples for each of these, okay? CO2, okay? When you look at CO2, you have 2 electron domains around the carbon, okay? And so if you're going to organize those 2 domains as far away from each other as possible, how would you separate those 2 domains from each other? How would you separate the 2 domains from each other to keep them as far away from each other as possible? Yes, Lucia. Okay, so what's the maximum angle you can create with 2 lines? 180. Yes, as far apart as each other as possible. It'd be 180. Okay. Now, what shape is that? A line. It's called linear. Okay, wow, y'all hesitated for that, and that's kind of that. I need to talk to your geometry teachers. Okay, it is linear. Okay, so if you have 2 electron domains, you have linear, and you can't have any other shapes with that because if one of them's a lone pair, it's still a line. Like if you get rid of this, it's still a line, right? So 2 domains, the only possible shape is linear. Okay. Let's say we have something like this. Okay. How many domains do we have around the boron? 3 domains. Okay. How do you orient 3 lines to maximize the angle from each other? How do you organize 3 lines so that you can maximize the distance from the angle? Yes, Sammy. A triangle. Wait, sorry, say it again. Oh yeah, yes. Trace the inside of a triangle that works here. So essentially what Sammy's saying is a Y. Right, exactly. It trace the inside of a triangle, like if the points of all of them converged into a center point. Because this angle is 120. And that's the maximum angle you can have between all of them. Okay. But I like what Sammy said because he said the shape of a triangle. Okay. And the name of this shape is trigonal planar. Because it's flat, exactly. It is on the flat plane, hence the name trigonal planar. Okay. Okay. All right. We're going to do the next one. Okay. CH4. Okay. 4 electron domains. Okay. This gets trickier because now we need 3 dimensions because having it all flat and 90 degrees like an axis is not the best way to draw it. And so what happens is we take it into the 3rd dimension. So now you've got kind of this 3-dimensional kind of tripod you want to imagine. I think that's the best way to kind of picture that. And each angle here is about 109.5 degrees. Okay. Yes. Yeah, I'm going to give you the angles for all the ones you need to know. If I don't give you an angle, you can assume you don't need to know it. Now, this name is a little bit more difficult, but it still makes sense. Because when you imagine this shape, if you connect 3 lines together, it makes a triangle. And it turns out it makes 4 triangle faces of the whole shape. Okay, hold on. What's the root for 4? Tetra. What's the shape? Tetrahedral. So tetrahedral translates to 4 faces. So this is a tetrahedral. Okay. Square planar is expanded octet, which we'll talk about in HL. Yeah. So these are tetrahedral. Now notice I have all bonds. Okay. So these are for SL, the 3 possible electronic geometries. These are the only three. So no matter what kind of shape you have, it doesn't matter if they're lone pairs or bonds. If you have a certain number of domains, that's your electronic geometry. It doesn't matter if they're lone pairs or bonds. If I have 3 domains, then it's going to be one of these 3. And I'm drawing it actually this way intentionally because you're going to find out the way I have you memorize it is based on knowing the electronic geometries and then taking stuff away from the electronic geometry to figure out the rest of the shapes. And you'll see how that works. So these 3 shapes I drew on purpose that way. And you'll kind of see what I mean. Okay. Now, let's say we have something like SO2. Okay. How many domains does SO2 have? 3. Why, Daphne? There's a lone pair on the S. So this is 3 domains. Okay, it's okay. This is how we learn. 3 domains. There's 2 bonds, 2 bonding areas, and 1 lone pair area. Okay. Now, the shape of it, the electronic geometry is still trigonal planar. But now let's pretend we replace one of these lines with a lone pair. Now it's no longer part of the shape. If you had to guess what shape this is, what is it? Bent. That's the shape. This is bent. Angular or bent. Okay. Does everyone see what I did there? So with molecular geometries, now the lone pairs are removed from the shape and all that's left is just the bonding pairs. So this is bent. Now the lone pair is still there. It just forces everything down and closer. So this angle ends up being 107. It would be more polar. I don't know if stability is something that we have to consider. Okay. What, Rachel? Okay. Now, let's look at something like NH3. Okay. Alexandra, how many domains are there? You sure?
Yes.
Okay. Just had to check. 4 domains. Okay. Because there's 3 bonds and 1 lone pair. So the electronic geometry starts like we did before. Tetrahedral. But now one of those lines is no longer present because it's in the place of a lone pair. So I erase that top line. What's the shape of the remaining lines now? Think of it in 3D. What's the shape of those 3 remaining lines? Yeah, and so it's a pyramidal. The bottom of a tripod is pyramidal. So this is trigonal pyramidal. You can just say pyramidal, by the way. I just am used to saying trigonal here as well because there's other pyramidals as well. Yeah, the square pyramidal, but usually you say square for that one. You don't say it for this one. So pyramidal is fine. Okay. Now, yes, Alexandra. These are the molecular geometries. Wait, what? Oh, yeah, that's him blending chemicals. Oh. No, he's not. So what he's making is he's making the chemical fuel for his rocket, like booster. And so he has to grind and mix potassium nitrate and sugar together to make a fine powder so that it combusts correctly. No. Like there's really no heat and stuff like that. Like you need a very, very strong amount of heat. The friction is not enough to cause an explosion and stuff like that. Okay. And then he packs it in and then ignites it. Okay. Now, the angle you start with is 109.5. Oh, I'm sorry. I wrote 107 here. I'm 117. I'm sorry. I was already getting ahead of myself. Every time you add a lone pair, the angle decreases by 3 degrees. That's a rule of thumb that you can stick with. So every time you add a lone pair to a structure, the bond angle decreases by 3 degrees because of the repulsion pushing everything down. So sorry, 117, not 107. So with tetrahedral to trigonal pyramidal, from 109.5, it goes to about 107. You could say 106.5, 107, that's fine. Okay. Now, water. Yeah, just about 3 degrees is fine. Okay. Water still has 4 domains, 2 bonding regions and 2 lone pairs. And so we start with the tetrahedral, that's the electronic geometry, and then we remove 2 lines. So remove this one, and remove this one. So what's left? Bent. Just a smaller angle, right, Sammy? So that angle you would guess here is about 104, 104.5. Yes. So yeah, like what they would probably do here is they'd have you draw the structure and then say, what shape is it? And then they'd probably ask you what the bond angle is to differentiate so you know which bend it was. Okay. So let me zoom out a little bit here. So for SL, these 3 are your electronic geometries. Every shape, every molecule that you deal with in SL falls under these 3 categories. But if they ask you for molecular geometry, it's possible that these or these as well. Okay, because if they're all bonds, then the molecular geometry is the same as the electronic geometry. But once they have lone pairs, the molecular geometry changes to this. I went vertically, yes. Did you not go vertically?
I didn't understand.
Oh, okay. It's okay. Remember, I always have an intention when I draw things the way I do on the notepad. So for SL, you need to know 3 electronic geometries and 6 total molecular geometries. But that sounds bad, but HL needs to know 15 or like 13 or 15. So they need to know these and then the other ones expand out 10. But I'm going to show you a trick, like I said, because here's the thing. I don't want you to memorize 6. Memorize 3. Minimize what you have to memorize. And that's why I drew them the way I do. Because if you know these 3 shapes, if you tell yourself, my 3 shapes are this, this, and this. If those are my 3 electronic geometries, every time I have a lone pair, I cover up 1 line. And that's all I have to do. And so don't memorize 6, memorize 3. Because if you know these 3, here's what you do. Trigonal planar. Take your finger, lone pair, okay, what's left? Bent. Tetrahedral. Cover 1 up, 3 down, trigonal pyramidal. Cover 2, what's left? Bent. That's how you minimize what you have to memorize. Don't memorize 6 shapes, memorize 3, and then just keep simplifying. What, Marina? Okay. And in higher level, you'll also do this. We'll start covering up lines and you'll be able to deduce all the shapes from that. Yes. Oh, yes, yes, sorry. So, sorry, Mateo asked rightly so. I will draw the bubble there. No, you're never gonna have to draw the shape yourself. Like the IB is never gonna have you draw these shapes, but I find drawing the electronic geometries helps you figure out the rest of the geometries. Okay. Okay, does that make sense? Okay, minimize what you have to memorize. And even with HL, I'm gonna tell you this, with HL, I'm gonna show you how you can figure out all the shapes with just 5 overall shapes instead of memorizing all 12. Because you can start with the first 5 electronic geometries and convert them step by step all the way down to every other possible shape. So there is like same idea with this. Now you just have more starting lines than you did the other one, and it will still work. So again, minimize what you have to memorize. Well, they're all molecular geometries, Alexandra. But the ones in blue are only molecular geometries, not electronic geometries. Yeah, if you have a lone pair or more, your molecular geometry will not be the same as your electronic geometry. Yeah. If you have a lone pair or more, your electronic geometry is not the same as your molecular geometry. But if they're all bonds, then the electronic and molecular are the same. I know this has been a long time since y'all seen this, so a little refresher course. Okay. We will go quickly through IMFs, and then we'll stop for SL, and then we'll continue to HL for the last hour. If you split it up into 2 columns, yes. Because there's not a lot to write, but if you try to follow, like, write all the way downward, you're going to have a lot of dead space on the right, so split it up into 2 columns. Okay. All right. And I'll do it on my notes as well. Okay. So the last thing I want to talk about today for SL, why is my line not straight? Okay, is polarity and IMFs. Okay. Now, the first thing we have to talk about on the left is bond polarity. Oh, wow, that line is like really not straight. Okay. I looked at the screen, I'm like, what? Okay. So bond polarity, okay? A bond polarity is the relationship in electronegativity between 2 bonds. So like if you have something like HCl, Cl is more electronegative. I believe it's like 3.0. Hydrogen's like 2.1. And so because chlorine is more electronegative, that bond is polar, and it's more negative this side and more positive this side. So each bond in a molecule has a certain polarity to it. Right? If it's just a 2-atom molecule, then the bond polarity is the same as the molecular polarity, because that's the only thing that contributes to the molecular polarity. So this is a polar covalent bond. Huh? Oh, these electronegativities. It is 2.1, right? Hold on a second. Where's my electronegativity table? You'll have this on. I'm just gonna yes, 2.1. Okay. I'll get rid of that once we get to that side, but I'm just gonna use it as a reference right now. Now, if you have something like this, carbon to hydrogen is 2.5 to 2.1, which is a difference of 0.4, which we still group as nonpolar covalent, meaning that they share electrons almost equally here. It's not exactly equally, but it is a spectrum of polarity that we have to worry about with bonding here. And so there's really not a bond polarity here. The difference in electronegativity, like I said, is a spectrum of type of bonds. If the difference of electronegativity, delta is a symbol for change, by the way. The change in electronegativity, if it's 0 to 0.4, we call that a nonpolar bond. If it's 0.4 to 1.7, we call that polar covalent. And 1.7 and higher is actually called ionic covalent. Yes, Penne. If they're the same atoms pulling in an tetrahedral, yes, they cancel out, which we're going to talk about molecular polarity in a little bit. Yes, you're right. Now, remember, this is a spectrum. So it doesn't suddenly become polar at 0.4. It becomes more and more polar-like until it reaches 0.4. So like in every textbook you see, the numbers change a little bit. Sometimes they say, oh, 0 to 0.5 is nonpolar, and then 1.6 is ionic. So the numbers themselves don't matter. Like there is some differences based on the review guides you use and stuff like that. Yes.
Well, that's like Polarity, for example, says 1.8, but like, what if it's like really close and you have to be second to like 1.7?
No, you shouldn't, like, at that point, if it's a metal and a non-metal, you assume it's ionic bonding at that point. But no, the IB shouldn't ever give you a bond that's close to one of the breakpoints. It should be very clearly within polar covalent or very clearly within ionic covalent. Yeah. Like they wouldn't give you a 1.6 or 1.7 to try to trick you. It would be like a 2.0 or it'd be like a 1.0, dead in the middle of the differences. Okay. Now, like Tene was saying, bond polarity has an effect on molecular polarity. Okay. And so when you talk about molecular polarity, you have to look at how the bond polarities are affecting the molecule. Okay. Sorry, Sam. I don't know if you're gonna run out of space here. Okay. So molecular polarity is the net direction of bond polarity. Okay. And so a molecule is polar if it has try to be careful here with SL versus HL. A polar molecule has a lone pair or a more polar bond. Okay. For SL, if you have a lone pair on your central atom, it's polar automatically. For HL, that is not true, which we'll talk about. But for SL, if you have a lone pair on your molecule, it's always going to be polar. And it's always going to be polar toward that lone pair because a lone pair trumps any electronegative atom. So if you have a lone pair, it's going to be a polar molecule. If they're all the same and there's no lone pairs, that's nonpolar. Okay. So nonpolar is same bonds around the central atom. Okay. So if you draw the Lewis structure out and there's no lone pairs and everything's the same around the central atom, that's nonpolar. Like CH4 or BF3 even is nonpolar because the B doesn't have lone pairs on it. So technically it's the same all around. Okay. Why does this matter? Because the polarity of the bond dictates the IMFs that are present in the molecule. Yes, Mateo.
So after 1.7, it becomes ionic.
Yes.
Why do you say ionic covalent?
Because nothing's ever truly ionic. Because they're still sharing the electrons, but it's just so unequal that if they split apart, then you would form ions from it. So like ionic is still technically covalent because there's never a time where the electron is like completely ripped off in the bonding process. It's when you break the atoms apart, then one rips the electron because it owns it so much of the time it becomes ionic. So it's still technically a covalent category. Okay. Right column of this. Okay. Huh? So the left column is polarity of bond and molecular. The right column, I'm going to do IMFs of covalent molecules. Okay. So this column is IMFs of simple covalent molecules. And what I mean by simple is molecules that are independent of each other. So like water is a simple covalent molecule because each water molecule consists of H2O. Or CH4 is a simple molecule. Things that aren't simple are like graphite or diamond because they're one giant molecule. They're not independent molecules of each other. Okay. So once you figure out the molecule's polar or nonpolar, that determines what the strongest IMF that's possible. If you have a nonpolar molecule, it's automatically the strongest force is London dispersion forces, which have a temporary dipole moment, meaning that the positive and negative aspects of the molecule fluctuate on and off constantly. And so the attraction is really, really weak. And these are dependent on mass. So the greater the mass of the molecule, the stronger the LDF forces. the best proof of that trend is going from fluorine, which is a gas, to chlorine, which is a gas, to bromine, which is a liquid, and then iodine is a solid. So within that group 17, the halogens become more solid as they go down because their masses are larger. So that tells you that you have a stronger LDF attraction forces. Let me zoom over this side. Let me clear that up. Liquid. Okay. Now, with polar molecules, they have LDF. So this is all inclusive. So you include the one above it. So polar molecules have LDFs, and usually that's the tiebreaker if everything else is the same. The LDFs are the tiebreaker. But for polar molecules, you have dipole-dipole attractions, which mean that every molecule has a positive and negative end permanently. So there is always an attraction between two molecules in that mixture. So there's always a positive and negative, so they're always attracted or repelled by each other. Okay. Now within the polar molecules, there is a stronger dipole-dipole attraction known as hydrogen bonding. And that occurs when H is bonded to N, O, or F. The reason why that is because when H is bonded to NO or F are the most electronegative elements and the smallest elements in the periodic table. So the pull is so strong that H becomes very, very positive, almost to the level of ionic attraction, which makes it much stronger. And so this is essentially a stronger dipole-dipole. And for example, like NH3 would have a very strong attraction to another NH3. And that is the hydrogen bonding. Because remember, IMFs are attractive forces between molecules. So when you say you boil something, you say you break forces of attraction. You don't break bonds. The molecule doesn't change. It just separates from each other, from the molecules around it. So don't ever say phase changes break bonds. They don't actually break bonds in covalent molecules. This is a covalent bond, which is much stronger. But the hydrogen bonding is the attraction between two molecules. Oh, one last thing, and then we'll stop for SL. These two are known as van der Waals forces. Okay. So what now the IB is very distinctive that says van der Waals forces are London dispersion and dipole-dipole forces. So you might look at old exams and they might accept van der Waals forces as an alternative for London dispersion forces. They're not the same anymore. Van der Waals includes both dipole-dipole and London dispersion. Yes, Alexandra. Well, you're just saying that polar molecules exhibit van der Waals forces, which includes both types of attractive forces, polar and nonpolar. That's all you're really saying. So like if they say, given this molecule, what types of forces are exhibited by this molecule? If it's a polar molecule, you could say van der Waals forces, or you could say dipole-dipole and London dispersion forces. They're the same. Okay. Whew. Okay. That is the end of the SL lesson for today. We're going to take about a 5-minute break here and then continue with HL for the rest of the session. I'm going to pause it right now. Okay, So HL session. What we're first going to do here is we're going to do Lewis structures with expanded octet because it doesn't really change what we were doing earlier, but it just adds kind of a new wrinkle to it. And so what you'll see is something like this, okay? Let's say you have something like XeF4, okay? We still follow the same idea. Xe is 8, fluorine is 7 times 4. That means you have 36 electrons available in your budget. Now, Xe is an octet, F needs an octet, so we draw it out. Okay? And we give everything an octet. But if we look at this octet, the issue is we only have 32 electrons in our test structure, which means we don't have enough electrons, which means that we have an expanded octet. Because what we don't factor in is that there must be lone pairs of electrons on the central atom that expand the octet. In fact, here it's 2 lone pairs. So there's actually 2 lone pairs on the xenon to create an expanded octet. And it's always only the central atom, by the way. You never have expanded octet on the outside atom. So whenever you're deficient in electrons, you put them on the central atom always. That's always true. So you can still follow the same formula. And so if you get fewer electrons in your test structure that has octets than what you have budgeted, every extra electron goes on the central atom. That's the only twist for HL. There's no changing in how you do things. It's just you add electrons instead of adding bonds. Okay. So the idea is this: because you can have expanded octet, that introduces more shapes for us. And so what that introduces to us is 5 electron domains and 6 electron domains. Okay. An example of 5 is PF5. Okay. Now, PF5 has 5 single bonds with F and no lone pairs. Okay. Now, coming up with the shape for 5 is kind of tricky because you have to be a little bit creative here, and not everything's the same angle. The way I want you to picture it is a line with a Y being dissected through it. Okay. So these bottom ones aren't in the paper. You know what? Maybe I'll draw it like this. Because since we've done wedge dash notation now, you can kind of understand that a little better. So it's in 3 dimensions. So the dash is going away from you and the wedge is coming toward you. So that's 3 dimensions. Okay. Now, this is 90 degrees, and each of these is 120 degrees. So there's 2 different angles you have to know for this. Okay. Now the shape, that's a little bit tricky. What you have to imagine for the shape is that imagine these points coming to a point like this. Okay. What shape is that blue shape that's given right there? Pyramid. And guess what? There's one on the top, there's one on the bottom. So guess what you call it? Bipyramidal. Sorry, I should have given you a chance to answer that. Bipyramidal. Trigonal bipyramidal if you prefer, but bipyramidal is fine because there's 2 pyramids stacked on top of each other to make that. So that's bipyramidal. Yes. So if you have 5, If you have 5 bonds, the electron is the same as molecular correctly. Every lone pair, though, changes the shape. Okay. Wait, hold on a second. It's just SF4, right? Hold on a second. 28, 34. Yeah, that's right. Okay, SF4. So SF4 looks like this. Now, that's not the shape. I just drew it like that. You don't have to draw your Lewis structures to imitate the shape. So it doesn't matter how you draw them as long as all the bonds are right. They don't care that you're drawing it the right shape. Okay. Let's start with the same structure we had before. Okay. 120 and 90. Okay. Now, of these lines, which line on average is the furthest away from the other lines in this structure? Which of these would be the furthest away on average from all the other structures? The top one, right? Because it's 90 and 90 and then 120 and 120. So overall, it would be furthest away from everything. So that's what becomes, our lone pair up there, okay? But I want you to picture the shape as just being this. Oh, I should change the color here because we were doing molecular geometries as green, sorry. Okay. What does that shape look like in highlighting? Seesaw. That's a seesaw shape, or sawhorse, okay? So visually, yeah, sawhorse is just another name for it. Like a sawhorse is like carpentry. They use sawhorses to put lumber on to cut. So they just call it a sawhorse. So either way is fine. Seesaw or sawhorse. If you look at different reference material, different materials, they'll call them either or. Yes, Ethon.
So I know that we did that last show, like now that you talked about like what the long hair does, so would you say like the straight lines?
Yes.
Would they be affected or would they
Yes. They are affected, but you don't have to represent that. But you are right. Ethon brings up a good point. Now, you don't have to know these angles as a number, but he's right. This lone pair is going to push stuff down close to each other. So now it's no longer 180 as a flat line. It's actually a little bit more than 180 or a little bit less than a 180 to each other. Actually, less than 180, I guess. I guess it depends on what reference you're talking about. Because like this angle is greater than 180 now because the lone pair is pushing everything down, right? If not. But you're not going to have to recite the angles for that. You don't have to know the angles for that. Okay. Okay, what's the example I want to do here? I believe ICL3. Let's see, ICL. Hold on, 21, 28. Wait, hold on. 12. Yeah, ICL3 is fine. Yes.
And okay, so now it's going to be 180 degrees, but the one that was like 120 degrees.
It can be less because they're going to be pushed closer to each other. Yeah. ICL3. Okay. Let's start with the structure we just had earlier with the lone pair there. Okay. Now remember, the lone pairs want to be as far away from each other as possible. Okay. So if that's the lone pair, what line is the furthest away from that lone pair? What next line is the furthest away from that lone pair? Which one? The one of the bottom legs, right. So we're going to erase this and make it a lone pair. Okay. What's the shape of what's highlighted now? It's not exactly because it's not 120. But if I had to choose a letter in the alphabet that it looks like, it's a T. It's T-shaped. Yes, it is called T-shaped.
I feel like these data has kind of just gave up now.
They got a little lazy for the shapes. Yes, you're right.
But how is that how is that two-shaped?
No, because remember, think of it like this, and then this leg going out like this. So when you look at it like from the top view, it's just a T.
Oh.
You see what I'm saying? So like, imagine it like this and like this, but then I rotate it towards you. See how it's T-shaped now? Yes or no, Mateo? Okay. But because, okay, if you want it easier, Mateo, actually, one of the things I'll suggest you do is that you could actually take away this one and have it like that.
Well, I mean, I get how it's two-shaped now. It's just like it's not.
It's you're gonna have to. It's a little bit challenged with some of these. Okay. Now, last one in this column. I3 minus. Oops, sorry. Okay. So we'll start with the shape we just did before. Okay. Now we have our two lone pairs, right? Which next line is the furthest away from the two lone pairs? So which next line is the furthest away from the two lone pairs? Ideas, Daphne? Okay, those are 90 degrees away from the lone pairs. Because you have to kind of imagine as y and then like this. They're 90 degrees. But the other line that I haven't gotten rid of yet is 120 from it. Yeah. So it's kind of weird seeing that 3 dimensions, but you end up taking this one out.
And when you added the two little bars to 5, is it like on purpose that they're both on top?
No, that doesn't matter.
Okay, maybe like one on top.
Yeah, that doesn't affect your shape though, because you still need to understand the shape. Oh, I didn't draw all the CLs there. Sorry, I didn't draw the third CL. Sorry. I got ahead of myself. There's 3 CLs there. Okay. So when you have 3 lone pairs here, what's the remaining shape? Linear. Because the lone pairs are all 120 degrees from each other, so they cancel each other out. So then all you're left with is a line. So it is a little bit tricky, but that's the way you want to see it. Okay. Questions about those shapes before we go on to 6? Okay. 6. When you have 6, like SF6, now you've got um, 4/5, depending on how far we want to go here. So it won't be longer than the other one. Okay. Now, 6 groups is the same as essentially 3 lines because you form 3 lines with 6 groups. What's the best way to organize 3 lines so that they're as far away from each other as possible? A what? A star, or think about it in math. How do you distribute 3 lines? X, Y, and Z axis. Like so, like everything's 90 degrees. So X, Y, and Z, that's as far away from each other as they can be. Okay. Now, it's a weird name because it doesn't seem very intuitive, but what you have to imagine is that each of these points comes together to make one face. You see how those 3 points come together to make a face? And then these make a face. And then the back makes a face. And it turns out there's 4 faces on the top and 4 faces on the bottom. Hence the name is, what's the prefix for 8? Octahedral. It's octahedral. A for effort, Mateo. Octahedral.
You know, that could be one of those, like, wrong, like in the test that you see like the wrong things that you have to correct.
Yeah.
Yeah, you could put that.
Oh, like bitetrahedral?
Yeah.
Yes, possibly. Yeah. Okay. I'm not going to test y'all on topic 4, so. Okay, octahedral. And these are all 90 degrees because it's X, Y, and Z. Okay, let me erase these purple lines here. Just wanted to see that. Now, SF5 minus. Okay, I'm not going to draw all these shapes now. I'm going to save some time. But I want you to start with, I'm going to draw it a little bit differently now. Because now that I think about it, this is probably better this way. Okay. Okay. So X, Y, and Z. Okay. Now, if I had to remove a line, if I had to change one line into a lone pair, does it matter which line I change into a lone pair? No, they're all 90 degrees from each other. So I'm going to do the easiest one, and I'm going to do the top one. Okay. Yeah, the X does move down a little bit, right? But if we're looking at the shape here, that X, imagine, is a base, and it comes to a point. Yeah, what base? A square. So this is a square pyramidal. That's the origin of that name. It's a square pyramid. XEF4. We start with the SF5 minus. Where would you put the second lone pair so that it's as far away from the other lone pair as possible? The bottom. So we get rid of that line. And that becomes a lone pair. What's the remaining shape here? Oh, but what shape does it form? Just like the previous one, what shape does it form? A square. But because you have 2 lone pairs pushing it flat, it's planar. It's square planar. Okay. Now you can keep going, and then it stops mattering which one you take apart. So you can do this. Okay. And what shape is this? T-shaped. And then you can go again. And you have what? Linear. Exactly. So those are the 1, 2, 3, 4, 5, 6, 7, 8, 9 additional shapes you have to know for HL as opposed to SL. So that's why it's 15 shapes. But again, minimize what you have to memorize. And yes, it may take you a little time to get used to this, but like I said, if you memorize all 5 electronic geometries, you can figure out all the molecular geometries by covering things up. And so the way I do it is I draw, I'm just going to do the HL here because we already did the SL. But so I draw HL like this. And then I draw, oops. Like this. Okay. So yes, you have to know trigonal, bipyramidal, and octahedral to start with, but I start from the top and then I start taking away ones. So this one You take one away, it's seesaw or sawhorse. You take a second one away, it's T-shaped. You take a third one away, it's linear. Oops. Here, you take one away, it's square pyramidal. You take the opposite one away, square planar. You take any of these away, doesn't matter. T-shaped, take the opposite one away, linear. So instead of memorizing 15 shapes, memorize 5 and then derive the rest of them from that. Okay. Oops, sorry, is there a chat in here? Oh, sorry, Maddie. I see what you said now. Yeah, I realized I didn't draw the CL, so I drew it already. Okay. Yes.
Can you go back to the square pyramidal of the state skeleton?
Yes.
Okay. So now is S5 minus 3 as 1 S7.
Correct.
And the that electron domain can be either 2 electrons or 1 electron.
No, it will be 2.
It will be 2, but now it's S5 minus 2.
Because S is 6, F is 7 each one. So that's 35 plus 6 is 41, plus the 1 electron is 42. And when you draw SF5, you end up with 40 electrons. So that extra pair goes on S.
So in comparison to SF6,
Yes.
how does adding only 1 more electron give you a
Because you got rid of an F. It's not just adding 1 more electron, you got rid of an F as well, Mateo.
Okay.
It's okay. I just love how Mateo's learning all the HL stuff. And he's taking the SL test. It's okay, it helps. I mean, it can't hurt you, Mateo. It might confuse you, but it can't hurt you. Okay. Another thing with Lewis structures here. Okay, I'm going to actually, what order do I want to do this in? We'll save formal charge to the end. Okay, what I want to talk about next is hybridization and sigma pi bonding. Okay, so with this, it's kind of twofold. Understanding sigma pi bonding allows you to figure out hybridization. Okay, what you need to understand, I want to make sure I have my exact definition here. Okay, a sigma bond, symbolized by that sigma symbol, is formed by the head-on overlap of atomic orbitals resulting in a concentrated electron density between nuclei. You're not going to have to memorize this definition, so don't freak out about it. But generally, all they're saying is when two atoms bond initially, the electron density is right between the two nuclei, the best place for it to be. Shortest distance, best optimal angle. Okay. But when you need additional bonds, like a double bond or a triple bond, you can only have one sigma bond between two elements. So the additional bonding has to occur in a different location than between the two nuclei because that's already occupied by the sigma bond. And that's where pi bonding comes into play. Is the sideways overlap of atomic orbitals resulting in a density above and below the plane of nuclei. okay? Again, you're not going to have to recite those definitions necessarily. Not word for word, but I would still know how to describe them. So sigma bond, head-on overlap, concentrated electron density between nuclei, and then pi bond is sideways overlap above and below the plane of the nuclei. So not word for word, but still kind of understand what it is, okay? So a good illustration of that is CO2, because CO2 contains both sigma and pi bonds. Every first bond between two atoms is a sigma bond, and every additional bond between two atoms is a pi bond. So here's an illustration of that. Okay. So this sigma bond right here, that's what they define by head-on overlap between two nuclei. So the nuclei is here, nuclei is here. The most direct linkage is a sigma bond between the two atoms. But because that space is already occupied in both of these atoms, when you need a second bond, it happens above and below, or in this case, side to side here. So the extra bonds happen with p orbitals that are parallel to each other, like here or like here in that. And that's a pi bond. Now, the pi bond is both the top and bottom together. So that's not like half a pi bond on top, half pi on bottom. The pi bond is the whole pink going from one to the other. Both top and bottom is one pi bond, and on the left, both pink lines are the whole pi bond as well. So a double bond consists of one sigma bond and a pi bond. A triple bond consists of one sigma bond and two pi bonds. Okay. Oh,
Wait, so this is CO2.
yes, this is CO2.
Or CO2 doesn't have triple bonds.
It doesn't. That's not a triple bond, Mateo. This is one double bond. This is the double bond here. This top and bottom is one bond.
So when a sigma bond is one pair of electrons, the pi bond is also one pair of electrons, and you have two pi bonds.
No, no, no. Oh, wait. Oh, sorry. On this side, this is one pi bond. Both the top and the bottom is one bond.
Oh.
Yeah, that's the confusing part. So this is one pi bond, even though it's two areas. Because if you look at the definition, it says the definition is top, above, and below. So the electrons can travel above or below in one pi bond. Okay. Okay. So why are these sigma? That's okay. Why are these sigma and pi bonds important? Because they help us explain something about shapes and our hybridization. Because the thing we haven't talked about yet is hybridization. Okay. Okay. A hybridization is the mixing of different types of atomic orbitals in an atom. Okay. Because here's the deal, and let me explain to you why hybridization is important. Do you need a pen, Mateo? Oh yeah. You're welcome. Were you gonna give her like part of the pen? Oh, okay. All right. That's fine. Mixing of different types of atomic orbitals. Okay, why is this important? Because here's the thing. If you remember from previous lessons, an s orbital is a sphere, and a p orbital can be one of three. It can be on the x-axis, the y-axis, and the z-axis. Okay, so these are all 90 degrees from each other, and this is a sphere right in the middle. The problem is this. When we look at CH4, and we actually measure the characteristics of CH4's bonds, what we see is equal bond lengths. okay, and equivalent angles, okay? The problem is that doesn't make sense if you're using s and p orbitals, because if you're using s and p orbitals, well, 3 of the hydrogens would be on p orbitals and 1 of them would be on s orbitals, so they couldn't be the same bond length and they couldn't be the same angles from each other because they have different angles. So hybridization explains why this is true. So what happens is these 4 orbitals combine together to make 4 equal mixed orbitals or hybrid orbitals, okay? And so what happens, yes, Mateo? Oh, I just labeled it wrong, sorry. Let me show you what that looks like. Okay. Sorry, yeah, so this should be py and px, yeah. Okay. So this is what happens in an atom. So an atom takes its s orbital and its p orbitals to create these 4 hybrid orbitals that are equivalent in energy and equivalent in bond length and equivalent in angle. And that's where the tetrahedral geometry comes from, because all 4 of them are the same now, and so they orient themselves in a tetrahedral shape. So hybridization helps explain why CH4 has that shape and why it has equal bond lengths, because you're not using s and p orbitals, you're using a hybrid of those orbitals called sp3 orbitals. And they're called sp3 orbitals because the orbitals are made of 1 s orbital and 3 p orbitals. So it's different than electron configuration where you say how many electrons are there. It's how many orbitals are being used for hybridization. Okay. Questions about that? So the end-all question is, well, how do I know the hybridization of an atom? Okay. So the hybrid orbitals are required for 1, sigma bonds, and 2, lone pairs. Pi bonds do not require hybrid orbitals. They actually use unhybridized p orbitals. So you do not count them in the hybridization of a structure. Okay. So for example, CH4 has 4 sigma bonds and 0 lone pairs. So it needs 4 hybrid orbitals, which we could also think of as electron domains as well, because you'll see the connection between those. The way you figure out what hybrid orbitals you need, I do it this way. Here are all the available orbitals to hybridize. If I need 4, I take the first 4 available, the lowest energy 4 available. So if I need 4, it's a hybridization of sp3. If I have something like CO2, how many sigma bonds does CO2 have? 2. How many lone pairs does the C have? 0. So that means you have 2 hybrid orbitals. So what's the hybridization around C? sp1. Or just sp, because you only need 2 hybrid orbitals there. Question, Ethan?
And how do you determine the superscript?
Oh, it's how many orbitals you need to complete the number of hybrid orbitals you need, Mateo. So like you see how I circled, I need 2 orbitals, right? For this, because I need 2 hybrid orbitals. So I take 1 s and I take 1 p. If I need 4 hybrid orbitals, I take 1 s and 3 p's. Hence why it's sp3.
But before we showed like that diagram of CO2,
Yes.
You guys already leave one of that's long pairs.
Okay.
I was wondering, like, I understand what you're doing now.
Yeah.
but, like, 'cause I remember like the SPs having like a different type of question. It was like,
The only type of question that they might have is, given this structure, how many total sigma bonds and how many pi bonds are there present?
yeah, it was like a structure.
Yeah, so in that, you look at the whole atom and that. So like, for example, what they'd ask there is like, they give you some organic molecule.
And then every bond is sitting on it.
Every double bond is a pi bond, correct? And so like, this is where organic structures kind of come into play, because yeah, you have 1, 2, 3, 4, 5, 6, 7, 8 sigma bonds. And then 2 pi bonds. So you would have to do that. Okay. Now, if I wanted the hybridization around this carbon right here, okay, how many hybrid orbitals do I need for that carbon? How many hybrid orbitals do I need for that carbon? 3. 3 bonding regions. No lone pairs. So that's 3 hybrid orbitals. So what would my hybridization be for that? sp2.
Okay, so we're doing hybridization of like a single.
Yes.
bond, not to give like a whole-
Correct. You would count sigma bonds and the pi bonds for the total thing, but every time you do hybridization, it's always of one individual atom. Yes. And sometimes they might have you label all 3 carbons in a structure, like multiple choice, but yeah, hybridization is just around one atom. Okay. Questions about that? And what you'll notice is this, last thing on this before we move to formal charge. You have sp1, sp2, sp3, sp3d1, sp3d2. Now, when does D happen? When you have an expanded octet, because you need more than 4 bonding regions. Okay. Okay. There's 9 minutes left. Okay. All right. Okay. Yeah. Okay. Now, here are your 5 possible hybridizations. You have 2 hybrid orbitals, 3 hybrid orbitals, 4 hybrid orbitals, 5, and 6 hybrid orbitals. No, but remember, if you remember from what I just said, oh, sorry, hybrid orbitals. You don't need to know that, Marina. Okay. Okay. Luckily, it's not an oral exam. Hybrid orbitals is the same as electron domains. So the hybridization of an atom is the same as its shape. It's the same as its electronic geometry. So if you have 2 hybrid orbitals, that's 2 electron domains, that's linear. If it's sp2, that's 3 electron domains, that's trigonal planar. If it's sp3, that's tetrahedral. And if it's 5, then it's trigonal bipyramidal. And if it's 6, it's octahedral. So you do need to understand that hybridizations lead to VSEPR shapes. And those are the 5 shapes that it leads to. So the number of hybrid orbitals is the same as the electron domains, which means that you can figure out the electronic geometries based on the hybridization. Okay. Okay. Questions? Okay. Last thing is formal charge. Hopefully this will take 5 minutes, but it may take a little bit longer. Okay. Formal charge. Used to determine optimal structure when multiple possibilities exist. Okay. So formal charge happens when, let's say you have a double bond and you have 2 different places that you can put it, but you don't know which one it goes on, and you have to try to figure out which one's the optimal shape. Okay. Formal charge as an equation, I do is this. It is valence electrons minus number of bonds minus lone electrons. So how many electrons are around the atom that are not bonded? And a lone pair means 2. Okay. So I say lone electrons specifically meaning that lone pair equals 2 electrons. Okay. So how does this happen? Okay. SCN minus 1. Okay, you don't need to know it's polyatomic, but it is a good example of this. Because when you do SCN minus 1, you have a lot of different combinations of bonds you could distribute. You could have it look like this. You could have it look like this. Or you could have it look like this. Because technically, the math means all three of these are possible. Okay, thank you. Thank you for the warning. Okay. This is his rocket fuel. That it's sugar and potassium nitrate, so it's very flammable if you heat it up. Not at the amount that he was doing he was doing the equivalent of a model rocket, so that was safe. Like he wasn't like burning huge chunks of it. He just made too much. That's the problem. Okay. No, not right now. We'll have to do a controlled disposal. Okay. As long as you're here. Okay. So here's how you do it. You have to calculate the formal charge of each atom in the structure. Okay. So in this one, sulfur has 6 valence electrons. According to this diagram, it has 3 bonds and 2 lone electrons. Because remember, each lone pair is 2 lone electrons. So it gets +1 as its formal charge. Carbon is 4 valence electrons minus 4 bonds and no lone pairs. No lone electrons, that's 0. Nitrogen is 5 valence electrons minus 1 bond minus 6 electrons is -2. Okay. This one here, S is 6 minus 2 bonds minus 4 valence electrons is 0. C is 4 minus 4 minus 0, 0. And N is 5 minus 2 minus 4 is -1. And last but not least, S is 6 minus 1 minus 6 is -1. C is 4 minus 4 minus 0. And then N is 5 minus 3 minus 2 is 0. So those are possibilities. Okay. The first thing you do is you want the formal charges as close to 0 as possible. Okay. Which means that rules out structure number 1 possibility because they're not as close to 0 as possible. Daphne? No, you want to treat them individually because they should all add up to the same overall charge because they're the same structure, right? So they should all add up to -1 overall. So that doesn't matter. We're looking at individual formal charges, which set is close to 0 as possible. Okay, so that means either the middle one or the right one is the correct structure. Okay, the tiebreaker is the negative charge is on most electronegative atom. Okay. Bye. Okay. You clean out the counter and stuff? Okay. See you, Nicholas. Bye. So these both have a -1 charge on one atom. One's on the N, one's on the S. So you go to look at the electronegativity, and I'll put it in here again to show y'all. And you find that S is less than N, which means that N should have the -1 charge, which means this is the ideal structure. And you do have to explain that. There are times in the IB exam where they'll give you the possible structures and they'll say, state and explain which one's the ideal structure. So you'd have to cite formal charge, calculate it, and then also explain why you have to tie break between two possible structures if there's two that are the same. Mateo. Oh, I thought I saw your hand up.
So what's TD?
Oh, tiebreaker. So you first eliminate anyone where it's not the same formal charges. And then if there are two that are identical except for where the negative charge is, the most electronegative one gets the negative charge. And opposite, if there's a positive charge, the least electronegative one gets the positive charge. I'm sorry?
So the negative or the positive charge will go on the most electronegative.
No. If it's negative, it goes on the most electronegative atom. If it's positive, it goes on the least electronegative atom. Yeah. Okay. Bye. All right, yeah, I'll break it down. Yes. Oh, that has to be given to you. Oh, if you add up all the formal charges? Oh, you have to be told that. Like, they won't just say SCN and you have to know it's minus. Like, they would tell you the formula has a negative charge in it. Like, you're asking about this, right? Like, how do scientists figure it out? Or, like, as a student, you would need to figure it out. But, like, I mean, what kind of happening is here is that this SCN ion is usually bonded to something else. And that helps dictate, that tells you that it's going to be a negatively charged. And depending on what it's bonded to, tells you what its charge is going to be overall. Yeah.
And how do you say that the negative charge is on the most electronegative? Negative.
Yeah. Okay. All right, questions? Okay. That is the end of today's lesson. Thank you for attending and thank you for staying over a couple minutes. And that's it.